Welcome to this Omega Tutorials Explainer. Today, we're tackling something that's absolutely foundational, but let's be honest, notoriously tricky: molecular hybridization. Now, you might be wondering, what's the actual problem we're solving here? Well, if you look at standard atomic orbitals, the basic s orbitals that are just simple spheres, and the p orbitals that look like little figure-8 dumbbells, they literally just don't explain the 3D structures of real-world molecules. If atoms only bonded using those basic shapes, the bond angles would be completely off and nothing would match what we actually observe in the lab. So, to bridge that gap between atomic theory and reality, we need a new model. We need to completely demystify hybridization.
Here is our game plan for today. First, we'll cover what hybridization actually is. Then, we'll break down the three main geometries: linear, SP, trigonoplanar, SP2, and tetrahedral, SP3. After that, we'll pull it all together in a handy comparison guide, and finally, wrap things up with some incredibly practical exam shortcuts.
Section 1. What is hybridization? Okay, let's dive right into this and tackle the core definition. At its most fundamental level, hybridization is all about the redistribution of orbital energy. When an atom is getting ready to form a bond, its atomic orbitals, which have slightly different energies like an s and a p orbital, actually mix together. This process effectively redistributes their energy and their shapes to give birth to entirely new orbitals. And these new orbitals, they have equivalent energy to one another, and they're mathematically optimized to form the strongest possible bonds. It's a real game changer for the molecule.
A really helpful way to visualize a hybrid orbital is to think about mixing paint. If you take a bucket of red paint, we'll call that our spherical s orbital, and mix it with a bucket of white paint, our dumbbell-shaped p orbital, you don't just get red and white stripes, right? You get an entirely new color, pink. And that's exactly what a hybrid orbital is. It's a brand new, intermediate shape that perfectly merges the traits of the original orbitals. And why do atoms go through all this trouble? It's beautifully simple, actually. Electrons absolutely hate each other. They repel. By creating these new hybrid orbitals, the atom can physically point its electron pairs as far away from each other as possible in 3D space, which stabilizes the whole shebang.
Section 2. Linear geometry, SP hybridization. Now that we've got the why down, let's look at our first specific flavor of mixing.
When a single spherical orbital hybridizes with one dumbbell-shaped p orbital, they blend to form two distinct sp hybrid orbitals. The result is this intermediate shape. You'll see a large lobe on one side and a tiny, smaller lobe on the other. It's neither perfectly spherical nor completely symmetrical like a standard p orbital. And this brilliantly illustrates what happens when you place those two newly formed sp hybrid orbitals together around a central nucleus. Remember our rule about electrons hating each other? Right. To minimize that repulsion, these two orbitals point in exact opposite directions. This creates a completely straight, linear geometry with a perfect 180-degree bond angle. It's literally the most efficient way to keep two electron groups as far apart as the universe will let them be. So here is the quick summary you'll absolutely want to lock into your memory for sp hybridization. You mix one s and one p orbital, which yields exactly two sp hybrid orbitals. Now, since standard atoms have three p orbitals in total, and we only used one, that leaves us with two unhybridized p orbitals left over, and those often get used later to form double or triple pi bonds. The geometry here is always linear, the bond angle is 180 degrees, and some classic examples you'll see are beryllium chloride or the triple bonded carbon in acetylene. Section 3. Trigonoplanar, SP2 hybridization. Let's step things up a notch and see what happens when we mix a bit more paint into our bucket. In this scenario, we're mixing one s orbital with two p orbitals. Take borane, or BH3 for example. Because three hybrid orbitals are created, they lay out perfectly flat in a single plane, pointing toward the corners of an equilateral triangle. We call this a trigonoplanar geometry. But check out that faded shape sitting straight up and down. Because we only use two of the three available p orbitals, there's one empty, unhybridized p orbital just sitting there. It rests at a perfect 90-degree right angle to the flat plane of the molecule. This empty orbital is super reactive and is a really crucial feature of molecules like borane and the methyl carbocation.
Let's break down the math for this one. You mix one s plus two p's, giving you three total sp² hybrid orbitals, with one unhybridized p orbital left over. To keep three electron groups maximally separated on a flat surface, you just divide a 360-degree circle by 3, which gives you a perfect 120-degree bond angle. You'll see this in BH3, like we just discussed, and in things like ethylene, where the carbons are double bonded. Section 4, tetrahedral sp3 hybridization. Moving right along to the third, and honestly probably the most common type of mixing you'll run into, especially if you're studying organic chemistry. The main driving force behind sp3 hybridization is having four distinct groups of electrons crowding a central atom. Now, a group can be a single bond, a double bond, or just a lone pair of electrons. When an atom is surrounded by four of these groups, it literally has no choice but to throw all of its outer orbitals, one s and all three p orbitals, into the mixing bucket to make room for them all. Since we mixed one s and three p orbitals, we yield four identical sp3 hybrid orbitals. And here's the kicker. There are 0 unhybridized p orbitals left over. They're all used up. So how do you arrange four identical things around a center point to keep them maximally separated? Well, they actually pop out of a flat 2D plane and form a 3D tetrahedron. The bond angle for this tetrahedral geometry is exactly 109.5 degrees. Methane, CH4, is the absolute classic textbook example of this gorgeous 3D structure. Section 5 Hybridization Comparison Guide. Let's move to our master summary table and see how all of this builds together, locking in those patterns. So the absolute coolest part is this mathematical pattern right here. Just look at the superscripts in the hybrid names. They literally give the answer away. For sp3, imagine a little 1 next to the s. 1s plus 3 p's equals 4 total hybrid orbitals. For sp2, 1 plus 2 equals 3 total hybrids. And for sp, 1 plus 1 equals 2. The number of electron domains you need to accommodate always matches the sum of the superscripts in the hybridization state. If you can just count your electron groups, you can instantly nail down the geometry and the bond angle. It's that easy. Section 6, Exam Shortcuts and Exceptions. And speaking of counting, let's introduce a highly practical shortcut designed to save you tons of time on your next exam.
Here is your bulletproof shortcut for figuring out hybridization in seconds. Step 1, count the number of attached atoms on your target central atom. And let me be super clear here. Count the atoms, not the bonds. A double or triple bond still only connects to one atom, so it just counts as 1. Step 2, add the number of lone pairs sitting directly on that same atom. Step 3, just match the sum. If your total is 4, it's sp3. If it's 3, it's sp2. If it's 2, it's sp.
Now, what's really interesting about this is how flawlessly this simple addition trick works across totally different molecules. Look at methane on the left. 4 attached hydrogens, 0 lone pairs. 4 plus 0 is 4, so boom, sp3. Now the carbocation in the middle. 3 attached carbons, 0 lone pairs. 3 plus 0 is 3, making it sp2. Finally, the nitrile group on the right. The carbon is triple bonded to the nitrogen. But remember the rule. It's only attached to one atom, the nitrogen, with 0 lone pairs. Actually, scratch that. Let's look at the nitrogen itself for a second. The nitrogen is attached to one atom, the carbon, and has 1 lone pair. 1 plus 1 equals 2. So that nitrogen is sp hybridized. It seriously works every single time. Well, okay, I should say it works almost every single time. Professors love to test exceptions, so here is the major trap you absolutely need to watch out for. If you have an atom with a lone pair sitting directly next to a pi bond, like in an amide or an enol, our little math shortcut will tell you it's sp3, but in reality, those atoms will rehybridize and drop down to sp2 instead. Why? Because by becoming sp2, they free up an unhybridized p orbital. They can then toss their lone pair into that empty p orbital, allowing it to overlap with the adjacent pi bond. This creates an incredibly stable, continuous system of moving electrons that we call resonance. So always watch out for lone pairs hiding next to double bonds. And that brings us to the end of our journey through molecular geometry. By understanding that hybridization is simply nature's brilliant way of mixing orbitals to keep electrons happy and spaced apart, you truly unlock the 3D architecture of the chemical world. With these shortcuts in hand and knowing exactly when to use them, are you ready to visualize the invisible and absolutely crush your next chemistry exam? Thanks for learning with Omega Tutorials. Keep visualizing, and we'll catch you in the next explainer.